Imagine this. It's 1977 and disco is dying, but two metal ambassadors are just beginning their epic journey into the cosmic unknown. While you were probably worried about gas prices and bell-bottom jeans, NASA was quietly launching what would become humanity's most successful interstellar detectives. But here's the thing that will make your morning coffee taste different. What these twin explorers found at the very edge of our solar system wasn't just unexpected. It was so bizarre, so fundamentally different from everything we thought we knew, that it forced scientists to rewrite textbooks and question decades of established physics. So settle in, forget about your schedule for a while, and let time slip away as we dive into one of the most mind-bending discoveries in human history. Because what Voyager found out there in the cosmic wilderness will change how you think about our place in the universe forever. The year was 1977, and the world was a different place. Elvis had just left the building permanently. Star Wars was captivating audiences for the first time, and most people thought the internet was something you might find tangled up in a fishing net. But in the sterile halls of NASA's Jet Propulsion Laboratory, something extraordinary was taking shape. A mission so ambitious, so perfectly timed with celestial mechanics, that it would only be possible once every 176 years. The Grand Tour, as it was originally conceived, would take advantage of a rare planetary alignment that wouldn't occur again until the 22nd century. Think about that for a moment. The last time the planets had lined up this way, Thomas Jefferson was president, and the idea of flying to the moon was pure fantasy. The next time it happens, your great-great-grandchildren might be living on Mars, wondering why their ancestors were so fascinated by something as primitive as rocket fuel. But budget cuts, those eternal killjoys of human ambition, forced NASA to scale back the Grand Tour to something more modest. Instead of visiting all the outer planets, they would focus on Jupiter and Saturn, with the possibility of extending to Uranus and Neptune if the spacecraft survived. Little did anyone know that this compromise would accidentally create the most successful deep space mission in human history. The Voyager program wasn't just about pretty pictures of planets, though those would certainly come. It was about answering fundamental questions that had plagued humanity since we first looked up at the stars and wondered what was out there. Questions like, what lies beyond the influence of our sun? Where does our solar system actually end? And perhaps most importantly, what secrets hide in that vast, dark ocean between the stars? Two identical spacecraft, each weighing about as much as a small car, were built to withstand the harshest environment known to exist, the vacuum of space with its radiation, extreme temperatures, and the constant threat of micrometeorite impacts. These weren't just machines, they were time capsules, carrying golden records with sounds and images from Earth, hoping that someday, somewhere, some form of intelligence might find them and wonder about the strange creatures who built them. Voyager 2 launched first on August 20th, 1977, followed by Voyager 1 on September 5th. The irony of their names, with Voyager 1 launching second but arriving first, would be just the beginning of the surprises these missions would deliver. As they began their long journey toward Jupiter, few people imagined they would still be operating nearly 5 decades later, sending back data from regions of space so remote that sunlight takes more than 22 hours to reach them. The early years of the mission unfolded like a carefully choreographed dance between human ingenuity and the laws of physics. As the two spacecraft approached Jupiter in 1979, they began transmitting images that made even seasoned astronomers gasp. Here was a world unlike anything in our earthbound experience, a roiling ball of gas and storm systems larger than our entire planet, surrounded by a retinue of moons that turned out to be worlds in their own right. Io, with its sulfur volcanoes painting the landscape in yellows and reds, challenged everything scientists thought they knew about geological activity in the outer solar system. Europa's icy surface, crisscrossed with mysterious lines and cracks, hinted at an ocean beneath that might harbor more water than all of Earth's seas combined, and Ganymede, larger than the planet Mercury, revealed itself to be a complex world with its own magnetic field, but Jupiter was just the opening act. As the Voyagers continued their grand tour towards Saturn, they were already traveling faster than any human-made objects had ever traveled before, using Jupiter's immense gravity as a cosmic slingshot to accelerate toward their next target. This technique, called a gravity assist, was so perfectly executed that it added years to the missions and opened up possibilities that had seemed impossible just months before. Saturn's system proved even more surprising than Jupiter's. The planet's rings, which had appeared as simple bands through Earth-based telescopes, revealed themselves to be incredibly complex structures, thousands of individual ringlets, some twisted into braids, others shepherded by tiny moons, all governed by gravitational forces so subtle that they resembled some cosmic clockwork designed by a mathematician with a sense of humor. And then there was Titan, Saturn's largest moon, shrouded in a thick orange atmosphere that hid its surface from view. The Voyager's instruments detected nitrogen and organic compounds in that atmosphere, the building blocks of life as we know it, existing in a deep freeze that preserved them like some natural laboratory waiting for the right conditions to spring into action. As Voyager 1 completed its encounter with Saturn in 1980, mission controllers faced a decision. The spacecraft could continue to Uranus and Neptune, following the path of its twin, or it could take a detour to get a closer look at Titan. They chose Titan, and that choice would prove pivotal to everything that followed. The close encounter with Saturn's moon sent Voyager 1 on a trajectory that would take it out of the plane of the solar system, heading toward interstellar space at an angle that would allow it to become the first human-made object to leave our solar system entirely. Voyager 2, meanwhile, continued the grand tour, becoming the only spacecraft ever to visit all 4 outer giant planets. Its encounters with Uranus in 1986 and Neptune in 1989 revealed worlds that defied expectation. Uranus, tipped on its side like a rolling ball, challenged theories about planetary formation. Neptune, despite being much farther from the Sun than Uranus, proved to be warmer and more dynamic, with winds reaching speeds of over 1,200 miles per hour, the fastest recorded in the solar system. But as spectacular as these planetary encounters were, they were really just preparation for the main event, the journey into the unknown regions beyond the planets where no human technology had ever ventured before. By the early 1990s, both Voyagers were traveling through a region of space that astronomers called the outer heliosphere, still within the Sun's influence, but increasingly dominated by forces and phenomena that existed nowhere else in the solar system. The Sun, you see, doesn't just emit light and heat. It constantly streams out a wind of charged particles that creates a vast bubble around our entire solar system, protecting us from the harsh radiation of interstellar space. This bubble, called the heliosphere, extends far beyond the orbits of the planets, but exactly how far and what lies beyond it remained one of the great mysteries of astronomy. Some scientists thought it might extend 50 or 60 times farther from the Sun than Earth's orbit. Others believed it could stretch twice that distance. A few maverick theorists suggested it might be even larger or might have an irregular shape influenced by our movement through the galaxy. As the Voyagers continued their journey through this uncharted territory, they began detecting phenomena that didn't match any of the theoretical models. The solar wind, that stream of particles from the Sun that should have been flowing smoothly outward, showed signs of turbulence and instability. Magnetic fields fluctuated in ways that suggested invisible structures and boundaries in what should have been empty space. In 2004, nearly 27 years after launch, Voyager 1 crossed what scientists called the termination shock, the point where the solar wind suddenly slows down as it begins to interact with the interstellar medium. This was like crossing the first major landmark in truly unexplored territory, and the data it sent back was immediately puzzling. The temperature beyond the termination shock was much higher than expected, millions of degrees, hot enough to strip electrons from atoms and create a plasma unlike anything found near Earth. but this wasn't the kind of heat you could feel. The particles were so few and far between that a human being would freeze solid in seconds. It was heat without warmth, energy without substance, a reminder that space operates by rules that have no parallel in human experience. More puzzling still, the magnetic field in this region didn't behave as predicted. Instead of the smooth, orderly patterns that theoretical models suggested, Voyager 1 detected a chaotic jumble of magnetic forces, as if invisible rivers of energy were flowing in multiple directions simultaneously. Some scientists began to suspect that the boundary between our solar system and interstellar space wasn't a simple, well-defined edge, but rather a complex transition zone full of unexpected physics. As Voyager 1 continued outward, it encountered another boundary that scientists hadn't even predicted, a region where the solar wind essentially stopped moving outward and began flowing sideways, as if it had hit some invisible wall. This region, which researchers dubbed the Helios sheath, extended much farther than anyone had anticipated, and the conditions there were unlike anything in the known universe. In the Helios sheath, particles from the sun mixed and mingled with particles from interstellar space, creating a sort of cosmic buffer zone where the physics of our solar system gradually gave way to the physics of the galaxy beyond. But the transition wasn't smooth or predictable. Instead, Voyager 1 detected sudden changes, unexpected spikes in radiation, and magnetic phenomena that seemed to come and go without warning. For years, scientists debated whether Voyager 1 had actually left the solar system or was still within some extended region of solar influence. The spacecraft's instruments detected changes that suggested it had crossed into interstellar space, but then other readings indicated it might still be within the heliosphere. It was like trying to determine the exact moment when day becomes night, clear in retrospect, but maddeningly ambiguous when you're experiencing it in real time. The confusion arose partly because scientists were looking for the wrong signals. They expected that crossing into interstellar space would be marked by a sudden change in the direction of the magnetic field as Voyager 1 moved from the sun's magnetic domain into the galaxy's magnetic environment. But the magnetic field direction barely changed at all, even as other measurements clearly indicated that something fundamental had shifted in the spacecraft's environment. Instead, the clearest sign that Voyager 1 had left the solar system came from an unexpected source: plasma waves. In 2012, a coronal mass ejection from the sun sent a shockwave racing outward through the solar system. When this wave reached Voyager 1's location, it caused the surrounding plasma to vibrate like a struck bell, and those vibrations revealed the density of the material around the spacecraft. The plasma was much denser than anything found in the outer solar system, confirming that Voyager 1 had indeed entered the interstellar medium. But this discovery raised more questions than it answered. If the magnetic field direction didn't change, what did that mean about the structure of the galaxy's magnetic environment? And why was the transition so gradual and complex rather than the sharp boundary that theorists had predicted? These questions became even more perplexing when scientists realized that the interstellar medium itself wasn't uniform. Voyager 1 was detecting variations in density, temperature, and magnetic field strength that suggested the space between stars was filled with structures and boundaries that no one had anticipated. It was as if the spacecraft had left one mystery only to encounter an even deeper one. The region that Voyager 1 had entered, scientists eventually realized, was what astronomers call the local interstellar cloud, a relatively dense region of gas and dust that our solar system happens to be passing through in its journey around the galaxy. This cloud, which extends for several light years in all directions, has properties that are significantly different from the average interstellar medium, and those differences were affecting everything about Voyager 1's environment. But perhaps the most shocking discovery came from what Voyager 1 didn't detect. For decades, scientists had assumed that cosmic rays, high-energy particles from deep space that constantly bombard our solar system, would become much more intense once a spacecraft left the protective bubble of the heliosphere. These cosmic rays, accelerated by distant supernovas and other violent cosmic events, should have created a harsh radiation environment that would quickly damage any unprotected spacecraft. Instead, Voyager 1 found that cosmic ray levels in the local interstellar cloud were actually lower than expected. The cloud itself seemed to be providing some protection from the most energetic particles, creating a sort of cosmic storm shelter that our solar system was passing through. This discovery suggested that the galaxy's radiation environment was far more complex and variable than anyone had imagined, with regions of relative calm interspersed with zones of intense activity. Even more intriguing were the low-energy cosmic rays that Voyager 1 began detecting after leaving the solar system. These particles, with energies just a few times greater than the solar wind particles, had never been seen before by any spacecraft. They seemed to be accelerated by some process in the nearby interstellar medium, but what that process might be remained completely mysterious. The magnetic field measurements added another layer to the puzzle. While the field direction remained surprisingly constant, its strength was about twice what scientists had predicted based on observations from Earth. This suggested that either the local interstellar cloud had unusual magnetic properties, or that the interaction between our solar system and the interstellar medium was creating magnetic effects that weren't accounted for in any theoretical model. As if these discoveries weren't puzzling enough, Voyager 1 also began detecting what scientists called anomalous cosmic rays, particles that seemed to be accelerated somewhere in the outer regions of our solar system, possibly at the boundary between the heliosphere and interstellar space. These particles had energies that were too high to be solar wind, but too low to be typical cosmic rays from distant sources. The leading theory was that these anomalous cosmic rays were neutral atoms from interstellar space that had drifted into the solar system, become ionized by solar radiation, and then been accelerated to high speeds by some unknown mechanism in the heliosphere's boundary regions. But the details of this process remained maddeningly unclear, and the particles' behavior didn't match what any theoretical model predicted. Meanwhile, Voyager 2, following a different trajectory through the outer solar system, was approaching its own encounter with the heliosphere's edge. When it crossed the termination shock in 2007, 3 years after its twin, it found conditions that were significantly different from what Voyager 1 had experienced. The shock was in a different location, the particle energies were different, and the magnetic field behavior showed distinct variations. This wasn't entirely surprising, since the heliosphere is a dynamic structure that changes in response to variations in solar activity and the solar system's movement through the local interstellar cloud. But the differences between the two spacecraft's measurements highlighted just how much scientists still didn't understand about this vast, invisible boundary that separates our solar system from the rest of the galaxy. As Voyager 2 continued outward through the heliosheath, it encountered many of the same puzzling phenomena that had mystified researchers studying Voyager 1's data. The solar wind didn't behave as predicted, the magnetic fields showed unexpected complexity, and the transition toward interstellar conditions was gradual rather than abrupt. But there were also unique features that suggested the heliosphere's structure was even more complex than the first spacecraft's data had indicated. In 2018, Voyager 2 finally crossed into interstellar space, becoming the second human-made object to leave the solar system. But its crossing was different from Voyager 1's in several crucial ways. The magnetic field direction did change, though not as dramatically as scientists had expected. The plasma density increased, confirming entry into the interstellar medium, and the cosmic ray environment showed variations that suggested the local interstellar cloud had different properties at Voyager 2's location than at Voyager 1's position. These differences were crucial for understanding the three-dimensional structure of the heliosphere and the interstellar medium beyond it. With two widely separated measurement points, scientists could begin to map out the shape of our solar system's boundary and understand how it interacted with the surrounding galactic environment. What emerged from this analysis was a picture of staggering complexity. The heliosphere wasn't a simple sphere or even an elongated bubble, as many models had suggested. Instead, it appeared to be a complex, dynamic structure with irregular boundaries, internal variations, and properties that changed depending on solar activity and our movement through the galaxy. The local interstellar cloud itself showed similar complexity. Rather than a uniform medium with consistent properties, it appeared to contain structures, boundaries, and variations that operated on scales from thousands of miles to several light years. Some regions were denser than others, some had stronger magnetic fields, and some showed chemical compositions that hinted at different origins or evolutionary histories. Perhaps most surprisingly, the boundary between our solar system and interstellar space wasn't really a boundary at all, but rather a transition zone that could extend for billions of miles. In this zone, solar and interstellar influences mixed and mingled in ways that created entirely new phenomena, particle populations that existed nowhere else, magnetic structures that formed from the interaction of different field systems, and plasma waves that carried information about conditions in regions too distant for direct observation. The cosmic ray environment in this transition zone proved to be particularly complex. Rather than the simple increase in high-energy particles that scientists had expected, both Voyagers found a layered structure where different types of cosmic rays dominated at different distances from the Sun. Some particles were clearly of solar origin, accelerated by magnetic processes in the heliosphere. Others came from nearby interstellar sources, possibly including the shock waves from ancient supernovas that had swept through the local interstellar cloud in the distant past. But there was also a population of particles that defied easy categorization. These seemed to be accelerated at the heliosphere's boundary itself, gaining energy from the collision between the solar wind and the interstellar medium. The process responsible for this acceleration remained mysterious, but it appeared to be creating a continuous source of energetic particles that filled the entire transition zone between solar and interstellar space. The magnetic field measurements from both spacecraft revealed another layer of complexity. While the overall field direction remained relatively constant, both Voyagers detected fluctuations and variations that suggested the presence of magnetic structures on many different scales. Some of these structures appeared to be related to the solar wind's interaction with the interstellar medium, while others seemed to be part of the galaxy's larger magnetic environment. Most intriguingly, there were hints that some magnetic structures might be related to our solar system's motion through the local interstellar cloud. As our entire solar system moves around the galaxy at a speed of about 500,000 miles per hour, it creates a bow shock in the interstellar medium, similar to the wake behind a boat moving through water. This bow shock might be creating magnetic effects that influence conditions throughout the outer heliosphere and beyond. The temperature measurements added yet another dimension to the puzzle. Both spacecraft found that the interstellar medium was much hotter than expected, not the cold, nearly empty space that many people imagine, but a plasma with temperatures of tens of thousands of degrees. This heat wasn't the result of some distant energy source, but rather a consequence of the low density of the interstellar medium itself. With so few particles to share the available energy, each particle ended up moving at extremely high speeds, creating temperatures that would vaporize any material substance instantly. But this hot plasma was also incredibly tenuous, with a density millions of times lower than the best vacuum achievable in laboratories on Earth. It was the environment that challenged intuition at every level, simultaneously hot and cold, energetic and empty, dynamic and stable. For spacecraft designed to operate in the relatively predictable environment of planetary space, it represented the ultimate test of engineering and endurance. The chemical composition of the interstellar medium provided clues about the history and evolution of our local galactic neighborhood. Both Voyagers detected traces of elements that could only have been created in the nuclear furnaces of massive stars, then dispersed into space when those stars exploded as supernovas. The relative abundances of these elements told a story of stellar birth, death, and rebirth that had been playing out in our region of the galaxy for billions of years. Some of the detected elements were particularly intriguing because they indicated that relatively recent supernova explosions had occurred in our cosmic neighborhood. These explosions, perhaps occurring within the last few million years, had not only enriched the interstellar medium with heavy elements, but had also shaped its structure and dynamics. The local interstellar cloud itself might be a product of these ancient stellar explosions, a bubble of hot gas that had cooled and condensed over millions of years. The data from both Voyagers also revealed that the interstellar medium was not static but was in constant motion, with flows and currents that operated on galactic scales. Our solar system was not just passing through a uniform cloud, but was encountering different streams and structures within that cloud, each with its own properties and history. This discovery suggested that the interstellar environment that future interstellar missions would encounter might be quite different from what the Voyagers were experiencing. As the years passed and both spacecraft continued their journey deeper into interstellar space, they began to detect phenomena that had never been observed before. There were radio emissions at frequencies that didn't match any known source, particle populations with energy distributions that defied explanation, and magnetic field variations that suggested the presence of structures too large and too distant to map with current technology. Some of these phenomena appeared to be related to the solar system's motion through the galaxy. As our heliosphere plowed through the local interstellar cloud, it created disturbances and interactions that generated effects visible to the Voyager's instruments. It was like watching the wake of a ship from inside the ship itself. The spacecraft were detecting the consequences of their own solar system's movement through space. Other phenomena seemed to be intrinsic properties of the interstellar medium itself. There were hints of turbulence on scales ranging from thousands of miles to light years, suggestions of magnetic structures that might be related to the galaxy's spiral arms, and evidence for particle acceleration processes that operated continuously throughout the local interstellar environment. Perhaps most surprisingly, both spacecraft began to detect what appeared to be organized structures in the interstellar medium, regions where the magnetic field, particle density, and temperature showed correlations that suggested some kind of underlying order. These structures were far too large to be mapped completely by the Voyagers, but their existence hinted at organizing principles in the interstellar medium that no theoretical model had predicted. The implications of these discoveries extended far beyond our understanding of the local galactic environment. They suggested that the space between stars was not the empty void that many people imagined, but rather a complex, dynamic medium filled with structure, activity, and phenomena that played crucial roles in the evolution of galaxies and the formation of new star systems. The cosmic ray discoveries were particularly significant for understanding the history and future of our solar system. The particles detected by both Voyagers carried information about stellar explosions, magnetic processes, and particle acceleration mechanisms that had operated in our galactic neighborhood over millions of years. By analyzing these cosmic messengers, scientists could reconstruct events that had occurred long before Earth formed and predict conditions that future space explorers might encounter. The magnetic field measurements provided insights into one of the most fundamental and least understood aspects of galactic structure. Magnetic fields play crucial roles in star formation, the dynamics of interstellar gas, and the propagation of cosmic rays throughout the galaxy. The Voyager's data represented the first direct measurements of these fields in the interstellar medium, providing ground truth for theories that had been based entirely on indirect observations. But perhaps the most profound implication of the Voyager's discoveries was what they revealed about the nature of boundaries in the universe. The edge of our solar system, which had seemed like it should be a simple, well-defined boundary, turned out to be a complex transition zone full of unexpected physics and phenomena. This discovery suggested that other cosmic boundaries, the edges of stellar systems, the boundaries between different phases of the interstellar medium, even the interfaces between galaxies might be similarly complex and dynamic. The longevity of both spacecraft had also exceeded all expectations. Designed to operate for 5 years, they had continued functioning for nearly 5 decades, their nuclear power sources still providing enough energy to operate critical instruments and maintain communication with Earth. This remarkable endurance had allowed scientists to study long-term variations in the interstellar environment and track changes that occurred over years and decades rather than just the brief moments of a typical space mission. As both Voyagers continued their journey deeper into interstellar space, they faced new challenges that tested the limits of 1970s technology. The radio signals they transmitted back to Earth were becoming increasingly weak, requiring larger and more sensitive antennas to detect. Their power supplies were slowly declining, forcing mission controllers to shut down non-essential systems to conserve energy for the most important measurements. But even as their capabilities diminished, the scientific value of their data continued to increase. Every day of operation in the interstellar medium provided new insights into an environment that no other human technology had ever explored. Each measurement helped refine models of galactic structure and evolution, and each discovery opened new questions about the nature of the space between stars. The data transmission delay had also become a significant factor in mission operations. Radio signals from Voyager 1 now took more than 22 hours to reach Earth, meaning that any command sent to the spacecraft wouldn't be received for nearly a full day, and the confirmation of that command wouldn't arrive back on Earth until almost 2 days after it was originally sent. This delay made real-time control impossible and required mission controllers to plan operations with unprecedented foresight and precision. Despite these challenges, both spacecraft continued to return data that challenged scientific understanding and revealed new aspects of the interstellar environment. They detected variations in cosmic ray intensity that correlated with changes in solar activity, suggesting that our sun's influence extended much farther into interstellar space than anyone had imagined. They measured fluctuations in the interstellar magnetic field that hinted at the presence of distant structures and processes operating on galactic scales. Most remarkably, they began to detect what appeared to be the interstellar equivalent of weather, variations in density, temperature, and magnetic field strength that suggested the local interstellar cloud was not a static structure, but a dynamic environment with its own patterns of change and evolution. These variations occurred on timescales ranging from days to years, indicating that the interstellar medium was far more active and complex than traditional models had suggested. The implications of these discoveries for future interstellar exploration were profound. Any spacecraft that ventured beyond our solar system would encounter an environment that was not only hostile and exotic, but also highly variable and unpredictable. The interstellar medium was not the empty void that early space pioneers had imagined, but rather a complex ecosystem of particles, fields, and phenomena that would challenge every aspect of spacecraft design and operation. The Voyager's journey had also revealed that our solar system's interaction with the interstellar environment was far more complex than anyone had anticipated. The heliosphere was not just a simple protective bubble, but an active interface where solar and galactic processes interacted to create entirely new phenomena. Understanding these interactions was crucial not only for space exploration, but also for understanding how our solar system had evolved over billions of years and how it might change in the future. As both spacecraft continued their eternal journey through the cosmos, they carried with them more than just scientific instruments and golden records. They had become humanity's first ambassadors to the galaxy, our earliest representatives in the vast ocean of space that separates the stars. Every measurement they transmitted back to Earth expanded our understanding of our place in the universe and revealed new aspects of the cosmic environment that surrounds us. The story of what Voyager detected at the edge of our solar system was ultimately a story about the limits of human knowledge and the endless capacity of the universe to surprise us. What had begun as a mission to explore the outer planets had become an ongoing investigation into the fundamental nature of space, time, and matter on the largest scales. Every discovery had raised new questions, every answer had revealed new mysteries, and every day of operation had pushed the boundaries of human understanding a little further into the unknown. In the decades since the Voyagers crossed into interstellar space, their discoveries had fundamentally changed how scientists thought about the structure and evolution of our galaxy. The interstellar medium was no longer seen as empty space punctuated by occasional stars, but rather as a complex, dynamic environment filled with structure, activity, and phenomena that played crucial roles in cosmic evolution. The magnetic fields detected by both spacecraft had proven to be particularly important for understanding galactic dynamics. These fields, stretching across light years of space, influence the motion of interstellar gas, the formation of new stars, and the propagation of cosmic rays throughout the galaxy. The Voyager's measurements provided the first direct evidence for theories about galactic magnetism that had been debated for decades. The cosmic ray discoveries had similar implications for understanding stellar evolution and galactic chemistry. The particles detected by both spacecraft carried information about nuclear processes that had occurred in massive stars millions of years ago, providing insights into the history of stellar birth and death in our local galactic neighborhood. Some of these particles had been accelerated by supernova explosions that had occurred before our solar system even formed, making them among the oldest messengers in the universe. But perhaps the most profound discovery was the realization that boundaries in the universe were not sharp divisions, but complex transition zones where different physical regimes gradually merged and interacted. This insight had implications not just for understanding our solar system's edge, but for comprehending interfaces throughout the cosmos, from the boundaries between different phases of matter in interstellar space to the edges of galaxies themselves. The Voyager's journey had also demonstrated the remarkable ability of human technology to operate in environments for which it was never specifically designed. Built with 1970s electronics and launched with 1970s rockets, both spacecraft had not only survived the harsh conditions of interstellar space, but had continued to function and return valuable data for decades longer than anyone had dared hope. This technological achievement was particularly remarkable given the extreme conditions that both spacecraft encountered as they traveled deeper into interstellar space. The temperature had dropped to just a few degrees above absolute zero, radiation levels fluctuated unpredictably, and micrometeorite impacts had gradually degraded some systems. Yet the core instruments continued to operate. The power systems continued to provide energy, and the communication systems continued to transmit data across billions of miles of space. The longevity of both missions had also allowed scientists to study phenomena that occurred on timescales much longer than typical space missions could observe. Variations in the interstellar environment that took months or years to develop could be tracked and analyzed, providing insights into the dynamics of the local interstellar cloud that would have been impossible to obtain from shorter missions. As the power supplies of both spacecraft continued to decline, mission controllers faced increasingly difficult decisions about which instruments to keep operating and which systems to shut down to conserve energy. Each choice represented a trade-off between different scientific objectives, and each decision brought the missions closer to their inevitable end. But even as the Voyagers approached the twilight of their operational lives, they continued to make discoveries that surprised and challenged scientists. The interstellar environment proved to be even more complex and dynamic than the decades of previous observations had revealed, with new phenomena appearing in the data as the spacecraft traveled deeper into previously unexplored regions of space. The scientific legacy of the Voyager missions extended far beyond the specific discoveries they had made. They had demonstrated the value of long-duration exploration missions, the importance of redundant measurements, and the power of human ingenuity to extract meaningful information from the most challenging environments. They had also shown that the universe was far more complex and interesting than anyone had imagined, and that even our local cosmic neighborhood contained mysteries that would take generations to fully understand. As both spacecraft continued their journey into the depths of interstellar space, they faced an uncertain but fascinating future. Their nuclear power sources would eventually decay to the point where they could no longer operate their instruments or maintain communication with Earth. When that day came, they would become silent ambassadors, carrying their golden records and the legacy of human exploration deeper into the galaxy. But the data they had already returned would continue to yield new insights for decades to come. The measurements they had made in the outer heliosphere and local interstellar medium had created a database of information that would serve as a foundation for future missions and theoretical studies. Every aspect of their journey through the boundary region between solar and interstellar space had revealed new phenomena and challenged existing understanding. The story of what Voyager detected at the edge of our solar system was ultimately a story about human curiosity and the relentless drive to explore the unknown. It was a reminder that the universe was far larger, stranger, and more wonderful than our everyday experience could possibly suggest. And it was a testament to the power of scientific exploration to expand the boundaries of human knowledge and reveal new aspects of our cosmic heritage. In the end, the Voyagers had done more than just explore the outer planets or measure conditions in interstellar space. They had fundamentally changed humanity's understanding of our place in the galaxy and revealed the rich complexity of the cosmic environment that surrounds us. They had shown that even the space between stars was filled with wonders that could challenge our assumptions and expand our imagination. And perhaps most importantly, they had demonstrated that the universe was not a collection of isolated objects separated by empty void, but rather a connected, dynamic system where every part influenced every other part. The boundary of our solar system was not an edge, but an interface, not an ending, but a transition to something even more vast and mysterious than what lay within. The deeper implications of the Voyager's discoveries became apparent as scientists began to integrate their findings with observations from other space missions and ground-based telescopes. The Hubble Space Telescope, the Spitzer Space Telescope, and eventually the James Webb Space Telescope all contributed pieces to a cosmic puzzle that the Voyagers had begun to reveal. What emerged was a picture of our local galactic environment that was far more interconnected and dynamic than anyone had imagined. The local interstellar cloud through which our solar system was traveling turned out to be part of a much larger structure called the local bubble, a region of space carved out by ancient supernova explosions that had occurred millions of years ago. This bubble, extending for hundreds of light years in all directions, was filled with hot, tenuous gas that showed the scars of stellar violence on an almost incomprehensible scale. The supernovas that had created this bubble hadn't just excavated empty space, they had filled it with the nuclear products of stellar death and created shock waves that were still propagating through the interstellar medium. Some of these shock waves were still detectable by the Voyager's instruments, appearing as subtle variations in cosmic ray intensity and magnetic field strength that carried information about explosions that had occurred before complex life evolved on Earth. But the local bubble wasn't isolated from the rest of the galaxy. It connected to other bubbles and structures in a vast network that astronomers called the interstellar medium's superbubble complex. This network channeled matter and energy between different regions of the galaxy, creating currents and flows that influence star formation, chemical evolution, and the overall structure of our cosmic neighborhood. The Voyager's measurements of the interstellar magnetic field provided crucial data for understanding how this network operated. The magnetic fields they detected weren't just local phenomena, but were connected to much larger structures that extended across the galaxy's spiral arms. These fields guided the motion of charged particles, influenced the dynamics of interstellar gas, and played crucial roles in the complex feedback processes that regulated star formation throughout the galaxy. As both spacecraft continued their journey deeper into interstellar space, they began to encounter variations in the interstellar medium that reflected our solar system's motion through these larger galactic structures. The properties of the local interstellar cloud weren't uniform, but showed gradual changes that suggested our solar system was approaching the boundary between different regions of the local bubble. These variations had profound implications for understanding the history and future of our solar system. Over millions of years, our solar system's journey around the galaxy had taken it through many different interstellar environments, each with its own properties and potential effects on the planets and their atmospheres. The climate history of Earth, the evolution of life, and even the rate of cosmic ray bombardment had all been influenced by these changing galactic conditions. The cosmic ray measurements from both Voyagers provided particularly detailed information about these historical variations. Different populations of cosmic rays carried signatures of different sources and acceleration mechanisms, creating a sort of fossil record of our galactic neighborhood's violent past. Some particles had been accelerated by supernova explosions that occurred millions of years ago, while others showed evidence of more recent acceleration in the boundaries and shock waves that filled the local bubble. The energy spectra of these cosmic rays revealed information about the magnetic field configurations that had accelerated them, the density of the material they had traveled through, and the timescales over which different acceleration processes had operated. By analyzing these spectra in detail, scientists could reconstruct the history of stellar explosions, shockwave propagation, and magnetic field evolution in our local galactic environment. But perhaps the most intriguing aspect of the cosmic ray data was what it revealed about the present-day acceleration processes operating in the heliosphere's boundary regions. Both Voyagers detected populations of particles that were clearly being accelerated at the interface between the solar wind and the interstellar medium, but the mechanisms responsible for this acceleration remained mysterious. Some scientists proposed that magnetic reconnection events, sudden rearrangements of magnetic field lines that released enormous amounts of energy, were responsible for accelerating these particles. Others suggested that turbulent processes in the boundary region created electric fields that could accelerate particles to high energies. Still others hypothesized that shock waves generated by the interaction between the solar wind and interstellar medium were responsible for the acceleration. The reality, as revealed by increasingly detailed analysis of the Voyager's data, appeared to involve all of these processes and more. The boundary region between the solar system and interstellar space was a complex, dynamic environment where multiple acceleration mechanisms operated simultaneously, creating particle populations with energy distributions that reflected this complexity. The magnetic field measurements from both spacecraft provided additional clues about these acceleration processes. The fields they detected showed signatures of magnetic reconnection events, turbulent cascades, and shockwave propagation that painted a picture of an extremely active and energetic boundary region. This wasn't the simple, static interface that early theoretical models had predicted, but rather a dynamic zone of ongoing physical processes that created new phenomena continuously. The plasma wave measurements added another dimension to this picture. Both spacecraft detected waves and oscillations that propagated through the boundary region, carrying energy and information about conditions in regions too distant for direct measurement. These waves provided a sort of seismic probe of the heliosphere's structure, revealing internal boundaries, density variations, and magnetic field configurations that couldn't be detected by any other means. Some of these plasma waves appeared to be generated by the solar wind's interaction with interstellar material, while others seemed to originate from processes deep within the interstellar medium itself. The wave frequencies, propagation characteristics, and energy distributions provided insights into the physical conditions throughout the boundary region and the processes that governed its evolution. The temperature measurements from both Voyagers revealed yet another layer of complexity in the boundary region's structure. Rather than the smooth temperature gradients that simple models had predicted, both spacecraft detected sharp transitions, localized heating events, and temperature inversions that suggested the presence of complex energy transport processes. These temperature variations weren't just academic curiosities. They had important implications for understanding how energy flowed between the solar system and the interstellar medium. The heating processes that created these temperature structures also influenced the dynamics of the boundary region, the acceleration of cosmic rays, and the propagation of disturbances between solar and interstellar space. As the years passed and both spacecraft continued to operate in the interstellar medium, they began to detect long-term variations that provided insights into the time-dependent behavior of the local interstellar cloud. The density, temperature, and magnetic field strength showed fluctuations on timescales ranging from months to years, suggesting that the interstellar medium was subject to processes that operated on much longer timescales than anything previously observed. Some of these variations appeared to be related to our solar system's motion through the local interstellar cloud. As the heliosphere moved through regions of different density and magnetic field strength, it created disturbances that propagated back through the boundary region and influenced conditions detected by the Voyagers. It was like watching the wake of a ship from inside the ship itself, but on a scale that dwarfed anything in human experience. Other variations seemed to be intrinsic properties of the interstellar medium itself. There were hints of large-scale circulation patterns, possibly driven by the pressure gradients created by ancient supernova explosions. There were suggestions of magnetic field oscillations that might be related to the galaxy's rotation and the complex dynamics of the spiral arms. Most intriguingly, there were indications that some of the variations might be related to processes occurring on even larger scales, perhaps the interaction between our local bubble and neighboring regions of the galaxy, or the effects of distant stellar explosions that were just beginning to influence conditions in our cosmic neighborhood. The chemical composition measurements from both spacecraft provided additional insights into these large-scale processes. The relative abundances of different elements in the interstellar medium told a story of stellar nucleosynthesis, supernova explosions, and chemical mixing that had been occurring in our galactic neighborhood for billions of years. Some elements, like hydrogen and helium, were primordial remnants from the Big Bang that had been cycling through stars and interstellar space since the early days of the galaxy. Others, like carbon, nitrogen, and oxygen, had been forged in the nuclear furnaces of massive stars and dispersed into space when those stars exploded. Still others, like iron and nickel, required the extreme conditions of supernova explosions to form and carried signatures of the most violent events in our galaxy's history. The isotopic ratios of these elements provided even more detailed information about the processes that had created and modified them. Some isotopes could only be formed by specific nuclear processes, making them powerful tracers of stellar evolution and supernova nucleosynthesis. Others were created by cosmic ray interactions with interstellar material, providing information about the history of high-energy particle acceleration in our galactic neighborhood. The dust measurements from both spacecraft revealed another important component of the interstellar medium that had significant implications for understanding galactic evolution. The tiny solid particles detected by the Voyager's dust sensors carried information about the condensation of elements in the cold depths of space, the formation and destruction of solid material in interstellar environments, and the transport of heavy elements throughout the galaxy. These dust grains weren't just passive tracers of interstellar processes. They played active roles in the chemistry and physics of the interstellar medium. They provided surfaces for chemical reactions that couldn't occur in the gas phase. They absorbed and scattered starlight in ways that influenced the thermal balance of interstellar space, and they served as condensation nuclei for the formation of molecules and eventually new stars and planets. The magnetic properties of these dust grains, revealed by their interaction with the interstellar magnetic field, provided additional information about their composition and origin. Some grains appeared to be silicate materials formed in the atmospheres of dying stars, while others showed signatures of carbonaceous compounds that might have been produced in more exotic environments. The trajectory data from both spacecraft provided a unique perspective on the three-dimensional structure of the interstellar medium that couldn't be obtained from any Earth-based observation. As the two Voyagers traveled along different paths through the local interstellar cloud, they sampled regions separated by billions of miles, allowing scientists to map out variations and structures on scales that approached the size of the entire cloud. This three-dimensional mapping revealed that the local interstellar cloud wasn't a simple uniform structure but contained internal boundaries, density variations, and magnetic field configurations that suggested a complex formation and evolutionary history. Some regions showed evidence of compression and heating that might have been caused by shock waves from distant supernova explosions. Others displayed signatures of cooling and condensation that indicated ongoing chemical and physical evolution. The relative motion between the two spacecraft also allowed scientists to measure the large-scale flow patterns within the local interstellar cloud. These flows provided information about the pressure gradients, magnetic forces, and gravitational influences that governed the cloud's dynamics and evolution. They also revealed connections to larger structures in the local bubble that suggested the cloud was part of a much more extensive network of interstellar material. As both spacecraft continued their journey deeper into interstellar space, they faced increasing challenges from the declining power output of their nuclear generators. The radioisotope thermoelectric generators that had powered both missions for decades were gradually losing their ability to produce electricity as their plutonium fuel decayed. This decline forced mission controllers to make increasingly difficult decisions about which instruments to keep operating and which systems to shut down. The power management strategies developed for the Voyager missions became studies in engineering optimization under extreme constraints. Every watt of available power had to be carefully allocated between essential systems like attitude control, data transmission, and critical scientific instruments. Non-essential systems were systematically shut down, and operating procedures were modified to minimize power consumption while maximizing scientific return. Despite these constraints, both spacecraft continued to return valuable data that expanded our understanding of the interstellar environment. The reduced instrument complement actually focused attention on the most important measurements and eliminated redundancy that had been built into the original mission design. In some ways, the power limitations forced scientists to think more carefully about which observations were truly essential and which were merely interesting. The communication challenges also intensified as both spacecraft traveled farther from Earth. The radio signals they transmitted became increasingly weak, requiring the use of larger and more sensitive antennas in NASA's deep space network. The data transmission rates had to be reduced to ensure reliable communication, which meant that the volume of information returned each day was much smaller than in the early years of the mission. But the scientific value of each bit of data had actually increased as the spacecraft entered previously unexplored regions of space. Every measurement provided new insights into an environment that no other human technology had ever encountered, and every day of operation extended humanity's reach deeper into the cosmos. The navigation and trajectory determination for both spacecraft had also become more challenging as they traveled farther from the sun. The gravitational influences that had been used to track their positions during the planetary encounters became increasingly weak, and other techniques had to be developed to maintain accurate knowledge of their locations and velocities. Radio tracking from Earth provided the primary means of navigation, but the increasing distance and communication delays made real-time control impossible. Trajectory updates and navigation solutions had to be computed days or weeks in advance, and the spacecraft had to operate autonomously for long periods without direct communication with Earth. The attitude control systems on both spacecraft faced particular challenges in the interstellar environment. The sun sensors that had been used to maintain orientation during the planetary encounters became less reliable as the sun appeared dimmer and smaller. Alternative methods had to be developed using star sensors and gyroscopes to maintain the precise pointing accuracy needed for communication with Earth and proper instrument operation. The thermal control systems also had to adapt to the extreme cold of interstellar space. Components that had been designed to operate in the relatively warm environment near the Sun now faced temperatures approaching absolute zero. Heaters powered by the declining electrical supply had to be carefully managed to keep critical systems operational while avoiding excessive power consumption. Despite all these challenges, both Voyagers continued to demonstrate the remarkable resilience of 1970s space technology. Components that had been designed for a 5-year mission continued to operate reliably after more than 4 decades in space. The careful engineering, redundant systems, and conservative design margins that had been built into both spacecraft proved their worth in an environment far more hostile than anything the original designers had anticipated. The scientific legacy of the Voyager missions extended far beyond their specific discoveries about the heliosphere and interstellar medium. They had demonstrated the value of long-duration exploration missions, the importance of building spacecraft to last far beyond their nominal mission requirements, and the power of international cooperation in advancing human knowledge. The technological innovations developed for the Voyager missions had applications that extended throughout the space program. The deep space communication techniques, navigation methods, power management strategies, and autonomous operations procedures pioneered by the Voyagers influenced the design of subsequent missions to the outer planets and beyond. The data analysis techniques developed to interpret the Voyagers' measurements had similar widespread applications. The methods used to extract information from weak signals, identify subtle patterns in complex datasets, and integrate measurements from multiple instruments became standard tools throughout space science and had applications in many other fields as well. The international collaboration that characterized the Voyager missions set a precedent for future space exploration projects. Scientists from around the world contributed to the mission's success, and the data were freely shared with the global research community. This open approach maximized the scientific return from the missions and established principles that continued to guide international space cooperation. The educational impact of the Voyager missions was equally significant. The spectacular images from the planetary encounters inspired a generation of students to pursue careers in science and engineering, while the ongoing discoveries in the interstellar medium continued to capture public imagination and demonstrate the value of basic scientific research. The philosophical implications of the Voyager's journey were perhaps even more profound than their scientific discoveries. These 2 small spacecraft had become humanity's most distant ambassadors, carrying messages from Earth to any intelligence that might someday encounter them in the depths of space. They represented human curiosity, ingenuity, and the desire to explore and understand the universe. The golden records attached to both spacecraft contained sounds, images, and information about life on Earth that would remain readable for millions of years. Even after the spacecraft themselves had long since fallen silent, these records would continue their journey through the galaxy, potentially outlasting human civilization itself and serving as monuments to our species' brief moment of cosmic exploration. When that day finally came, both Voyagers would become silent sentinels, continuing their journey through interstellar space without the ability to report their discoveries back to Earth. They would join the small number of human artifacts that had achieved true cosmic longevity, joining the ranks of objects that would outlast not only their creators, but potentially the entire solar system that had given them birth. But even in silence, the Voyagers would continue to explore. Their trajectories would carry them past other star systems over the next few 100,000 years, and eventually they might encounter environments and phenomena that would dwarf even the discoveries they had already made. They had become permanent citizens of the galaxy, representatives of Earth traveling roads that no human being would ever walk. The scientific data they had already returned would continue to yield new insights for generations to come. The measurements they had made during their passage through the heliosphere and into interstellar space had created an unprecedented database of information about the boundary between solar and galactic environments. Every aspect of their journey had contributed to humanity's understanding of our place in the cosmos. Future missions to the outer solar system and beyond would build upon the foundation that the Voyagers had established. The interstellar probe mission, currently in development, would follow in their footsteps, but with much more advanced instruments and capabilities. The New Horizons spacecraft, which had already explored Pluto, was also heading toward interstellar space and would eventually provide a third sampling point for understanding the heliosphere's structure and the properties of the interstellar medium. But none of these future missions could diminish the achievement of the Voyagers or the fundamental importance of their discoveries. They had been the first to venture beyond the edge of our solar system, the first to sample the interstellar medium directly, and the first to reveal the true complexity and richness of the space between the stars. They had opened a new chapter in human exploration and understanding that would continue to unfold for as long as our species maintained its curiosity about the universe. The deeper scientists delved into the Voyager data, the more they realized that what appeared to be empty space was actually teeming with invisible architecture on scales that dwarfed human comprehension. The interstellar medium wasn't just a collection of random particles drifting through space, but rather a complex web of interconnected structures that revealed the galaxy's hidden organizational principles. The magnetic field measurements from both spacecraft had revealed something extraordinary. The interstellar magnetic field wasn't chaotic or random, but showed signs of large-scale organization that extended across hundreds of light years. This field appeared to be connected to even larger structures that astronomers were only beginning to understand, magnetic highways that channeled matter and energy along the galaxy's spiral arms and influenced the formation of new star systems. These magnetic structures operated like invisible rivers in space, guiding the motion of charged particles and creating currents that could transport material across vast distances. The cosmic rays detected by both Voyagers weren't just random particles bouncing around the galaxy. They were following these magnetic pathways, creating a sort of galactic circulatory system that connected distant regions and enabled the exchange of matter and energy on scales that approached the size of the entire Milky Way. The implications of this discovery were staggering. It meant that our solar system wasn't an isolated island in space, but rather a connected part of a vast galactic ecosystem. The particles that bombarded Earth's atmosphere, the elements that formed the planets, and even the conditions that allowed life to evolve had all been influenced by processes operating on galactic scales and connected through this invisible magnetic infrastructure. The plasma wave data from both spacecraft provided additional insights into how this galactic system operated. The waves they detected weren't just local disturbances, but appeared to be part of a galaxy-wide communication network that carried information about distant events and processes. Shock waves from supernovas that had exploded thousands of light years away could still be detected in the plasma oscillations measured by the Voyagers, like echoes from cosmic catastrophes that had occurred long before human civilization began. These plasma waves also revealed the presence of structures in the interstellar medium that were invisible to conventional telescopes. Boundaries between regions of different density and temperature created interfaces that supported specialized types of wave propagation, much like the way ocean currents create invisible boundaries that affect wave patterns on Earth's surface. But these cosmic boundaries extended for light years and influenced processes that operated on timescales of millions of years. The temperature measurements from both spacecraft had uncovered another layer of complexity in the interstellar environment. The local interstellar cloud wasn't uniformly heated, but contained temperature gradients and thermal structures that revealed ongoing energy transport processes operating on enormous scales. Some regions showed evidence of heating that could only be explained by magnetic reconnection events, sudden rearrangements of magnetic field lines that released energy equivalent to millions of hydrogen bombs every second. These magnetic reconnection events weren't rare occurrences, but appeared to be happening continuously throughout the interstellar medium, creating a sort of background level of violent activity that was completely invisible to human senses, but played crucial roles in determining the properties of the space between stars. The energy released by these events influenced everything from the acceleration of cosmic rays to the chemical reactions that occurred on interstellar dust grains. The dust measurements from both Voyagers had revealed an entire ecosystem of solid particles that existed in the supposedly empty space between stars. These weren't just simple specks of matter, but complex assemblages of different materials that carried the chemical signatures of stellar explosions, planetary formation processes, and exotic nuclear reactions that occurred in the most extreme environments in the galaxy. Some dust grains showed evidence of having been forged in the atmospheres of dying red giant stars, where temperatures and pressures created conditions unlike anything found elsewhere in the universe. Others appeared to have been created in supernova explosions, where the incredible energies involved had synthesized heavy elements and then blasted them into space at speeds approaching a significant fraction of the speed of light. But perhaps most intriguingly, some dust grains showed isotopic signatures that suggested they had originated outside our solar system entirely, visitors from distant star systems that had somehow made their way across the vast gulfs of interstellar space. These alien particles carried information about stellar processes and planetary formation in other parts of the galaxy, providing glimpses into cosmic environments that no human technology could ever directly explore. The chemical composition data from both spacecraft had revealed that the interstellar medium was far from chemically uniform, but showed variations that reflected the complex history of stellar evolution in our galactic neighborhood. Different regions contained different mixtures of elements depending on the types of stars that had lived and died in each area and the timescales over which mixing processes had been able to operate. Some regions showed enhanced abundances of elements like oxygen and neon, suggesting they had been enriched by the explosions of massive stars that had burned through their nuclear fuel relatively quickly. Others displayed elevated levels of iron and nickel, indicating contamination by Type 1a supernovas, thermonuclear explosions of white dwarf stars that had been triggered when they accumulated too much material from companion stars. The isotopic ratios of these elements provided even more detailed information about the nuclear processes that had created them. Some isotopes could only be produced by specific types of stellar explosions or nuclear reactions, making them powerful tracers of the violent events that had shaped our galactic neighborhood. The relative abundances of different isotopes told stories of stellar birth, evolution, and death that had been occurring for billions of years. But the most shocking discovery was that some of the isotopic ratios detected by the Voyagers didn't match what would be expected from normal stellar nucleosynthesis processes. There were hints of exotic nuclear reactions that could only occur under conditions even more extreme than those found in supernova explosions, possibly in the collision of neutron stars or in the vicinity of black holes where gravitational forces could compress matter to densities that defied comprehension. The cosmic ray data had revealed an entire zoo of high-energy particles that were being accelerated by processes operating throughout the local interstellar cloud and beyond. Different populations of cosmic rays showed different energy spectra, different chemical compositions, and different arrival directions that provided clues about the acceleration mechanisms and source regions responsible for creating them. Some cosmic rays appeared to be relatively local products, accelerated by shock waves and magnetic processes operating within a few hundred light years of our solar system. These particles carried information about recent supernova explosions, stellar winds from massive stars, and the complex dynamics of the local bubble structure that surrounded our solar neighborhood. Others showed signs of having traveled much greater distances, possibly from the galaxy's central regions or from distant spiral arms where conditions were very different from those in our local environment. These far-traveled particles provided insights into galactic-scale processes and phenomena that couldn't be studied by any other means. But perhaps the most puzzling cosmic rays were those that showed evidence of having been accelerated multiple times during their journey through the galaxy. These particles appeared to have encountered several different acceleration regions, each of which had added energy and modified their properties. The result was cosmic ray populations with complex energy distributions that reflected the layered history of their galactic odyssey. The magnetic field measurements from both spacecraft had revealed that the interstellar magnetic field wasn't static, but showed variations and fluctuations that occurred on timescales ranging from hours to years. Some of these variations appeared to be related to the solar system's motion through the local interstellar cloud, as the heliosphere encountered regions with different magnetic properties and created disturbances that propagated throughout the boundary region. Other magnetic field variations seem to be intrinsic properties of the interstellar medium itself, possibly related to turbulent processes that operated on scales ranging from thousands of miles to several light years. These turbulent motions created magnetic field fluctuations that could accelerate particles, generate plasma waves, and influence the propagation of cosmic rays throughout the local galactic environment. The most intriguing magnetic field variations were those that appeared to be periodic, suggesting the presence of organized structures or processes that operated on regular timescales. Some periodicities seem to be related to our solar system's orbital motion around the galaxy as we encountered different environments during our 230 million year journey around the galactic center. Others showed periodicities that might be related to the galaxy's spiral structure or to oscillations in our position relative to the galactic plane. Every 33 million years, our solar system passes through the densest part of the galactic disk, encountering higher concentrations of stars, gas, dust, and cosmic rays. The magnetic field variations detected by the Voyagers might be providing early warnings of these encounters, decades or centuries before their effects became apparent in other ways. The plasma density measurements had revealed that the local interstellar cloud wasn't a uniform structure but contained internal boundaries, gradients, and variations that suggested a complex formation and evolutionary history. Some regions showed densities that were significantly higher than the galactic average, possibly indicating compression by shock waves from nearby stellar explosions or gravitational focusing effects related to the cloud's motion through the local bubble. Other regions displayed unusually low densities that might represent cavities carved out by stellar winds or supernova explosions that had occurred more recently than the events that created the overall local bubble structure. These cavities provided natural laboratories for studying plasma physics under conditions that couldn't be reproduced in any terrestrial experiment. The boundaries between regions of different density weren't sharp interfaces, but rather transition zones that could extend for thousands of miles and showed evidence of ongoing mixing and mass exchange processes. These transition zones supported specialized types of plasma waves and magnetic phenomena that played important roles in the overall dynamics of the interstellar medium. The velocity measurements from both spacecraft had revealed that the local interstellar cloud wasn't moving through space as a rigid body, but showed internal motions and flows that indicated complex dynamics operating within the cloud itself. Some regions appeared to be expanding, possibly as a result of heating by nearby stars or shockwave interactions, while others showed signs of contraction that might be leading to the formation of new dense structures. These internal motions created velocity gradients and shear flows that could generate turbulence, accelerate particles, and influence the magnetic field structure throughout the cloud. The result was a dynamic, evolving system that was continuously reshaping itself in response to internal processes and external influences. The most significant external influence was the motion of our entire solar system through the cloud at a speed of about 26 kilometers per second. This motion created a bow shock in the interstellar medium that extended far beyond the heliosphere itself and influenced conditions throughout a region that might encompass several light years. The bow shock wasn't a simple, symmetric structure, but showed complex three-dimensional variations that reflected the non-uniform properties of the interstellar medium and the complex shape of the heliosphere itself. Different parts of the shock encountered different conditions and created different types of disturbances that could be detected in the Voyager's measurements of magnetic fields, plasma waves, and energetic particles. The radiation environment measurements had revealed that the space between stars wasn't the cold, empty void that many people imagined, but rather an active, energetic environment filled with various forms of electromagnetic radiation and high-energy particles. The background radiation levels were much higher than anything found in the inner solar system, creating challenges for both biological systems and electronic equipment that venture into interstellar space. Some of this radiation came from distant sources like quasars, pulsars, and active galactic nuclei that pumped enormous amounts of energy into the interstellar medium. Other components were generated by more local processes like cosmic ray interactions with interstellar gas and dust, which created secondary particles and electromagnetic radiation that added to the overall background. The most surprising component of the radiation environment was what scientists called anomalous X-ray emission, high-energy photons that appeared to be generated by some unknown process in the local interstellar cloud itself. These X-rays didn't match the spectrum expected from any conventional astrophysical source and suggested that exotic physical processes might be operating in the interstellar medium. The time variability of the radiation environment provided additional clues about the processes responsible for creating it. Some components showed variations that correlated with solar activity, suggesting that our sun's influence extended much farther into interstellar space than previously thought. Others displayed periodicities that might be related to our orbital motion around the galaxy or to intrinsic variations in the interstellar medium itself. The gravitational measurements from both spacecraft, while less precise than the electromagnetic and particle observations, had detected subtle variations that provided insights into the mass distribution within the local interstellar cloud. These measurements were extraordinarily challenging because the gravitational effects of interstellar material were incredibly weak compared to the sun's influence, but they provided unique information about the total amount of matter in the cloud and its spatial distribution. The mass estimates derived from these measurements suggested that the local interstellar cloud contained significantly more material than could be accounted for by the observed gas and dust alone. This missing mass might consist of dark matter, exotic particles that interact only weakly with ordinary matter and electromagnetic radiation, but still exert gravitational influences on their surroundings. Alternative explanations for the missing mass included populations of very small solid particles that were too tiny to be detected directly by the Voyager's dust sensors, or perhaps concentrations of cold, dense gas that didn't emit enough radiation to be observable from Earth. Each possibility had different implications for understanding the structure and evolution of the interstellar medium. The navigation data from both spacecraft had provided unprecedented information about the three-dimensional structure of the heliosphere and its interaction with the interstellar medium. By tracking the precise positions and velocities of both Voyagers as they traveled through the boundary region, scientists could map out the shape of the heliosphere and understand how it was influenced by the properties of the surrounding interstellar environment. This mapping had revealed that the heliosphere wasn't the symmetric, comet-like structure that many models had predicted, but rather a complex, irregular shape that reflected the non-uniform properties of the local interstellar cloud. Different parts of the heliosphere extended different distances into interstellar space, depending on the local density, magnetic field strength, and velocity of the interstellar material they encountered. The asymmetries in the heliosphere's shape had important implications for understanding how our solar system interacted with the interstellar medium and how that interaction might change as we continued our journey through the local interstellar cloud. Some models suggested that our solar system might eventually encounter regions of the cloud with very different properties, which could significantly alter the heliosphere's structure and the radiation environment throughout the solar system. The long-term stability of both spacecraft had allowed scientists to study phenomena that occurred on timescales much longer than typical space missions could observe. Multi-year variations in the interstellar environment could be tracked and analyzed, providing insights into the dynamics of processes that operated on scales of decades or centuries rather than the hours or days typical of most astrophysical observations. Some of these long-term variations appear to be related to changes in solar activity that influenced the size and shape of the heliosphere. During periods of high solar activity, the increased solar wind pressure pushed the heliosphere's boundaries farther into interstellar space, while during solar minimum periods, the reduced pressure allowed the interstellar medium to compress the heliosphere to smaller dimensions. Other long-term variations seem to be intrinsic properties of the interstellar medium itself, possibly related to the passage of shock waves from distant supernova explosions or to our solar system's motion through regions of the local interstellar cloud with different properties. These variations provided a sort of time-lapse movie of interstellar dynamics that revealed processes operating on scales that dwarfed anything accessible to direct human observation. The data processing and analysis challenges associated with the Voyager missions had pushed the boundaries of computational science and data analysis techniques. The weak signals transmitted by both spacecraft required sophisticated error correction algorithms and noise reduction techniques to extract meaningful information from the electromagnetic interference and background noise that contaminated the data. The long-time series of measurements from both spacecraft created datasets that were too large and complex to analyze using conventional techniques. New methods had to be developed for identifying subtle patterns and correlations in multidimensional datasets that contained millions of individual measurements spanning decades of observations. The statistical analysis of the Voyager data had revealed correlations and patterns that weren't immediately obvious from examining individual measurements. Cross-correlations between different types of observations had uncovered connections between phenomena that had previously seemed unrelated, providing insights into the underlying physical processes responsible for creating the observed variations. Machine learning and artificial intelligence techniques had been applied to the Voyager datasets to identify patterns that might have been missed by conventional analysis methods. These computer algorithms could process vast amounts of data and identify subtle signatures that human analysts might overlook, leading to the discovery of new phenomena and the refinement of existing theoretical models. The calibration and validation of the Voyager instruments over their extended lifetimes had required continuous monitoring and adjustment to account for the effects of radiation damage, thermal cycling, and component aging. Many instruments were still operating decades after their design lifetimes had expired, but their characteristics had changed in ways that had to be carefully understood to maintain the accuracy of the scientific measurements. The environmental conditions in interstellar space were more benign in some ways than the harsh radiation environment near Jupiter, but they presented unique challenges that the instrument designers had never anticipated. The extreme cold caused some materials to become brittle and change their electrical properties, while the low particle densities created conditions where electrostatic charging could build up to dangerous levels. The communication systems on both spacecraft had been pushed far beyond their design specifications as the distance to Earth increased and the available power declined. The radio transmitters were operating at power levels much lower than originally planned, and the antennas had to be pointed with extraordinary precision to maintain the narrow beam required for efficient communication across billions of miles. The data compression algorithms used to maximize the scientific return from the limited communication bandwidth had evolved throughout the missions as new techniques were developed and implemented. Early in the missions, relatively simple compression schemes were used, but as the available bandwidth decreased, more sophisticated algorithms were employed to squeeze every bit of information from the precious communication opportunities. The ground-based receiving systems had also undergone continuous upgrades to maintain communication with both spacecraft as their signals became weaker and more difficult to detect. The antennas in NASA's Deep Space Network had been expanded and their sensitivity improved, while new signal processing techniques had been developed to extract coherent signals from noise levels that would have made communication impossible using older technology. The international cooperation that characterized the Voyager missions had extended beyond the initial spacecraft design and construction to encompass data analysis, theoretical interpretation, and mission planning throughout the extended phases of both missions. Scientists from around the world had contributed expertise in specialized areas and had access to the data streams from both spacecraft. This global collaboration had accelerated the pace of discovery and ensured that the scientific return from both missions was maximized. Different research groups had focused on different aspects of the data, and their combined efforts had produced a more comprehensive understanding of the interstellar environment than any single institution could have achieved. The educational and outreach programs associated with the Voyager missions had inspired generations of students and had communicated the excitement of scientific discovery to millions of people around the world. The missions had become symbols of human exploration and scientific achievement that transcended national boundaries and cultural differences. The story of what Voyager detected at the edge of our solar system was ultimately a story about the endless frontier of human knowledge and the universe's infinite capacity to surprise and challenge our understanding. Every discovery had revealed new mysteries, every answer had led to new questions, and every day of operation had pushed the boundaries of human experience a little further into the vast unknown that surrounds us all. As both spacecraft continued their eternal journey through the cosmos, they carried with them not just the instruments and records that humans had built, but also the hopes and dreams of a species that had dared to reach beyond its home planet and explore the infinite frontier of space. Their discoveries at the edge of our solar system had opened a new chapter in the human story, one that would continue to unfold as long as we maintained our sense of wonder about the universe and our determination to explore its deepest mysteries. The legacy of both Voyagers extended far beyond their specific scientific discoveries to encompass the broader human enterprise of exploration and discovery. They had demonstrated that even with limited resources and technology, human ingenuity could achieve results that seemed impossible at the outset. They had shown that the universe was far more complex and interesting than our terrestrial experience could possibly suggest, and they had opened pathways for future exploration that would continue for centuries to come. Perhaps the most profound revelation from the Voyager missions was the discovery that our entire concept of boundaries in the universe needed to be fundamentally reconsidered. The edge of our solar system wasn't a wall or a cliff, but rather a complex transition zone where multiple physical regimes gradually merged and interacted. This insight forced scientists to reconsider other cosmic boundaries that had previously been thought of as simple divisions between different regions of space. The heliopause itself turned out to be not a single boundary, but a complex region containing multiple distinct zones, each with its own characteristic physics and phenomena. There was the termination shock, where the solar wind first encountered the resistance of the interstellar medium. Beyond that lay the heliosheath, a turbulent region where solar and interstellar influences battled for dominance. And finally, there was the heliopause proper, where the solar wind's influence finally gave way to the interstellar medium. But even this wasn't a sharp transition, but rather a gradual changeover that could extend for millions of miles. Each of these regions harbored phenomena that challenged existing theoretical frameworks and required new approaches to understand. The termination shock wasn't the simple, well-behaved boundary predicted by early models, but rather a dynamic, fluctuating interface that could move inward and outward by billions of miles in response to changes in solar activity and interstellar conditions. The heliosheath revealed itself to be a cauldron of exotic physics, where magnetic field lines could become tangled and twisted into configurations that had no analog in any terrestrial laboratory. Particles could be trapped and accelerated in these magnetic labyrinths for years or decades before finally escaping into either the inner solar system or the interstellar medium beyond. The heliopause itself showed properties that defied simple categorization. In some regions, it appeared to be a relatively sharp boundary where solar wind particles were suddenly replaced by interstellar material. In other areas, the transition was so gradual that it was difficult to determine exactly where one regime ended and the other began. These variations in the heliopause's properties reflected the complex three-dimensional structure of both the heliosphere and the surrounding interstellar medium. The local interstellar cloud wasn't uniform, but contained density variations, magnetic field fluctuations, and velocity gradients that created a constantly changing environment for the heliosphere to interact with. The discovery of these boundary complexities had profound implications for understanding similar interfaces throughout the universe. Other stellar systems must have their own versions of the heliosphere, each shaped by the unique properties of its central star and the particular characteristics of the interstellar environment it was traveling through. The variations detected by the Voyagers suggested that no two stellar systems would have identical boundary structures, making each one a unique laboratory for studying plasma physics under extreme conditions. The galactic scale implications of the Voyager discoveries were equally significant. The local interstellar cloud was just one small component of the much larger local bubble, which itself was part of an even more extensive network of interconnected structures that extended throughout the galaxy's spiral arms. The magnetic fields, particle populations, and energy transport mechanisms detected by both spacecraft were components of systems that operated on scales approaching the size of the entire Milky Way. The cosmic ray measurements from both Voyagers had revealed that these particles weren't just random debris from stellar explosions, but were actually integral components of a galaxy-wide energy transport system. High-energy particles accelerated in one region of the galaxy could travel for millions of years before depositing their energy in completely different environments, creating connections between distant regions that would otherwise have no direct influence on each other. This galactic-scale energy transport had implications for understanding everything from star formation rates to the chemical evolution of different galactic regions. Cosmic rays could influence the temperature and ionization state of interstellar gas clouds, affecting their ability to collapse and form new stars. They could also transport newly synthesized heavy elements from their birthplaces in massive stars to regions where they could be incorporated into the next generation of stellar and planetary systems. The magnetic field measurements from both spacecraft had revealed that these cosmic magnetic highways weren't just passive conduits for particle transport, but were active participants in galactic dynamics. Magnetic fields could channel the motion of interstellar gas, influence the propagation of shock waves from supernova explosions, and even affect the overall rotation pattern of the galaxy itself. The complexity of these magnetic structures was staggering. They operated on scales ranging from the size of individual star systems to the dimensions of entire spiral arms, with smaller structures nested within larger ones in a hierarchical pattern that resembled the organization of matter on all scales throughout the universe. Understanding this magnetic hierarchy was crucial for comprehending how galaxies evolved and maintained their structure over billions of years. The plasma wave discoveries had revealed another layer of this galactic connectivity. The waves detected by both Voyagers weren't just local disturbances, but were parts of a galaxy-wide communication network that could carry information about distant events across vast expanses of space and time. A supernova explosion in one spiral arm could generate plasma waves that would eventually propagate throughout the entire galaxy, carrying information about the explosion's energy, chemical composition, and temporal evolution. This wave-based information transport system operated much faster than the physical transport of particles or magnetic field changes, allowing different regions of the galaxy to know about distant events relatively quickly. The waves could also interact with local plasma conditions in ways that amplified or modified their characteristics, creating complex interference patterns that encoded information about multiple distant sources simultaneously. The temperature and density measurements had revealed that the interstellar medium wasn't just a passive repository for material ejected from stars, but was an active participant in galactic chemical evolution. Different regions showed chemical signatures that reflected their unique histories of stellar birth, evolution, and death. But there was also evidence for large-scale mixing processes that could transport material between widely separated regions. These mixing processes weren't simple diffusion, but involved complex flows and currents that could operate on timescales of millions to hundreds of millions of years. Material ejected from a supernova explosion in one part of the galaxy could eventually find its way to completely different regions where it would influence the formation of new stars and planets. This galactic recycling system was one of the key mechanisms that enabled the universe to evolve from the simple hydrogen and helium that emerged from the Big Bang to the complex chemical diversity we observe today. The dust measurements had revealed an entire ecosystem of solid particles that played crucial roles in this galactic chemical evolution. Dust grains weren't just passive tracers of stellar explosions, but were active sites where chemical reactions could occur under conditions that were impossible in the gas phase. The surfaces of these microscopic particles provided catalytic sites where simple molecules could combine to form more complex compounds, including some of the organic molecules that would later become the building blocks of life. The formation and destruction of dust grains was itself a complex process that involved multiple competing mechanisms. Grains could be created in the atmospheres of dying stars, where cooling gas condensed into solid particles that were then ejected into space by stellar winds. They could also be destroyed by shock waves from supernova explosions or by the intense radiation fields near young, hot stars. The size distribution of dust grains reflected this balance between formation and destruction processes, with different environments favoring the creation of particles with different characteristics. Some regions contained mostly small grains that were efficient at absorbing and scattering ultraviolet radiation, while others were dominated by larger particles that could survive longer in harsh radiation environments. The isotopic composition of dust grains provided detailed information about their formation mechanisms and evolutionary histories. Different types of stellar explosions produced distinctive isotopic signatures that could be preserved in dust grains for millions of years, creating a sort of fossil record of stellar nucleosynthesis processes that had operated throughout the galaxy's history. The Voyager's ability to sample these dust populations directly had provided ground truth for theoretical models of dust formation and evolution that had previously been based entirely on indirect observations. The agreement between theory and observation in some areas was remarkably good, confirming fundamental aspects of stellar evolution theory, but there were also significant discrepancies that pointed to gaps in our understanding of these processes. The radiation environment measurements had revealed that interstellar space was bathed in electromagnetic radiation, spanning an enormous range of frequencies, from long wavelength radio waves to high-energy gamma rays. This radiation field wasn't uniform, but showed complex variations that reflected the distribution of different types of sources throughout the galaxy. Some components of this radiation field were clearly associated with specific astrophysical objects like pulsars, supernova remnants, and active galactic nuclei. Others appeared to be more diffuse backgrounds created by the collective effects of many faint sources or by processes operating throughout the interstellar medium itself. The most puzzling component was a diffuse X-ray background that seemed to permeate the entire local interstellar cloud but couldn't be explained by any conventional astrophysical mechanism. The spectrum and intensity of this radiation suggested that it might be produced by some exotic process involving dark matter interactions or previously unknown plasma physics phenomena. The variability of the radiation environment provided additional clues about its origins and the processes responsible for creating it. Some components showed rapid fluctuations that indicated nearby sources or propagation effects related to the turbulent structure of the interstellar medium. Others displayed long-term variations that might be related to our solar system's motion through regions with different radiation field characteristics. The gravitational measurements, while limited by the sensitivity of the Voyager instruments, had provided tantalizing hints about the mass distribution within the local interstellar cloud and the possible presence of exotic forms of matter that didn't interact electromagnetically. The total mass inferred from these measurements exceeded what could be accounted for by the observed gas and dust by a significant margin, suggesting the presence of additional components that remained invisible to conventional observations. One possibility was that the missing mass consisted of dark matter, hypothetical particles that interacted only through gravitational forces and composed the majority of matter throughout the universe. If dark matter was present in the local interstellar cloud, it would have important implications for understanding both the local galactic environment and the broader distribution of matter throughout the cosmos. Alternative explanations for the missing mass included populations of very small dust particles that were below the detection threshold of the Voyager's instruments, concentrations of cold molecular gas that didn't emit enough radiation to be detectable, or perhaps even more exotic possibilities like primordial black holes left over from the early universe. The navigation and trajectory data from both spacecraft had provided unprecedented information about the gravitational environment in the outer solar system and beyond. By tracking the minute variations in both spacecraft's trajectories, scientists could map out mass concentrations and gravitational anomalies that would be impossible to detect by any other means. This gravitational mapping had revealed that even the outer regions of our solar system contained structures and mass distributions that weren't predicted by conventional models. There were hints of gravitational effects that might be caused by undiscovered objects in the outer solar system, though these effects were so small that they required years of careful analysis to detect and characterize. The long-term stability of both missions had enabled studies of gravitational phenomena that operated on timescales much longer than typical spacecraft missions. Multi-year variations in gravitational effects could be tracked and analyzed, providing insights into the dynamics of the outer solar system and the nearby interstellar environment that would be impossible to obtain from shorter observations. The precision required for these gravitational studies had pushed the boundaries of navigation and orbit determination techniques. The positions and velocities of both spacecraft had to be known with extraordinary accuracy to detect the tiny gravitational effects being studied, requiring sophisticated modeling of all the forces acting on the spacecraft and careful correction for systematic errors and biases. The technological achievements represented by the continued operation of both Voyagers decades beyond their design lifetimes had implications that extended far beyond space exploration. The engineering principles, design philosophies, and operational techniques developed for these missions had influenced everything from satellite design to deep space communication systems to autonomous vehicle navigation. The power management strategies developed for both spacecraft had pioneered techniques that were later adopted throughout the space industry. The ability to operate complex systems at extremely low power levels while maintaining critical functionality had become essential for many types of space missions, especially those involving small spacecraft or missions to very distant destinations. The communication systems on both Voyagers had demonstrated the feasibility of maintaining contact with spacecraft at interstellar distances, providing crucial experience for planning future missions to other star systems. The techniques developed for extracting weak signals from noise, maintaining precise antennae pointing over long periods, and maximizing data transmission efficiency had all contributed to the advancement of deep space communication technology. The autonomous operation capabilities developed for both missions had shown how spacecraft could operate for extended periods without direct human control, making intelligent decisions about resource allocation, system health monitoring, and scientific observations. These capabilities had become essential for missions to the outer planets and beyond, where communication delays made real-time control impossible. The data analysis and interpretation challenges posed by the Voyager datasets had driven innovations in computational science, signal processing, and statistical analysis that had applications throughout the scientific community. The techniques developed for extracting information from noisy, incomplete datasets had found applications in fields ranging from climate science to medical imaging to financial analysis. The international collaboration that had characterized both missions from their inception had set precedents for large-scale scientific cooperation that had influenced subsequent space exploration projects. The model of open data sharing, joint analysis efforts, and coordinated planning had become standard practice for major space science missions and had contributed to the development of truly global scientific communities. The educational and cultural impact of both missions had extended far beyond their scientific achievements to inspire generations of students and communicate the excitement of discovery to people around the world. The iconic images from the planetary encounters, the romantic notion of messages to aliens carried on golden records, and the ongoing story of humanity's first ambassadors to the stars had captured public imagination in ways that transcended cultural and national boundaries. The philosophical implications of the Voyager discoveries were perhaps even more profound than their scientific significance. These missions had fundamentally altered humanity's perspective on our place in the universe by revealing the true complexity and connectivity of the cosmic environment that surrounds us. We were not isolated inhabitants of a small planet orbiting an ordinary star, but rather participants in a vast, dynamic system that extended throughout the galaxy and beyond. The boundary discoveries had shown that the universe was not composed of discrete, isolated objects separated by empty space, but rather consisted of overlapping, interconnected systems where every component influenced every other component. This insight had implications that extended far beyond astrophysics to influence our understanding of complex systems throughout science and society. The longevity of both missions had demonstrated humanity's capacity to create artifacts that could outlast not only their creators, but potentially entire civilizations. The Voyagers would continue their journey through interstellar space long after the last human being had died, carrying their golden records and the memory of our species into the cosmic future. This realization had profound implications for how we thought about legacy, permanence, and our responsibilities to future generations. The Voyagers represented humanity at its best, curious, ingenious, ambitious, and hopeful about the future. They embodied our species' greatest aspirations and would serve as monuments to human achievement for millions of years to come. As both spacecraft continued their eternal voyage through the cosmos, they remained active participants in the ongoing story of human exploration and discovery. Every measurement they transmitted back to Earth continued to expand our understanding of the universe and reveal new aspects of the cosmic environment that no previous generation had been able to explore. The story of what Voyager detected at the edge of our solar system was ultimately a story about the limitless potential of human curiosity and the endless capacity of the universe to surprise and inspire us. It was a reminder that there would always be new frontiers to explore, new mysteries to solve, and new wonders to discover, and it was a testament to the power of science and exploration to unite humanity in a common quest for knowledge and understanding that transcended all the boundaries that divided us on Earth. The Voyagers had shown us that we were citizens of the galaxy, participants in a cosmic story that was far grander and more magnificent than our everyday experience could possibly suggest. They had opened our eyes to the true scale and complexity of the universe, while simultaneously demonstrating that even the most distant frontiers were within reach of human ingenuity and determination. In the end, the greatest discovery made by both Voyagers might not have been any specific scientific finding, but rather the demonstration that the universe was knowable, explorable, and filled with wonders that rewarded those bold enough to venture into the unknown. They had proven that the boundaries of human knowledge were not fixed limitations, but rather temporary horizons that could always be pushed a little further into the infinite expanse of space and time. The subtle art of interstellar archaeology that the Voyagers had pioneered revealed layers of cosmic history that stretched back billions of years. Every particle they detected, every magnetic field fluctuation they measured, every plasma wave they recorded was a messenger from the deep past, carrying information about events that had occurred long before our solar system even existed. The interstellar medium wasn't just empty space between stars, but rather a vast library containing the accumulated history of stellar birth, evolution, and death written in languages of physics that we were only beginning to learn to read. The isotopic signatures embedded in cosmic ray particles told stories of stellar nucleosynthesis that had occurred in massive stars whose light had faded billions of years before Earth formed. Some of these particles had been created in the first generation of stars that formed after the Big Bang, when the universe contained only hydrogen, helium, and trace amounts of lithium. These ancient stellar furnaces had forged the first heavy elements and scattered them into space when they exploded as supernovas, seeding the interstellar medium with the raw materials that would eventually become planets, asteroids, and the complex chemistry of life itself. Other particles carried signatures of more recent stellar catastrophes, including some that might have occurred within the last few million years in our immediate galactic neighborhood. These relatively recent explosions had shaped the local bubble structure that surrounds our solar system and created many of the density variations, temperature gradients, and magnetic field configurations that the Voyagers were still detecting decades after entering interstellar space. The magnetic field measurements had revealed fossil traces of ancient magnetic structures that had been frozen into the interstellar medium by the extremely low electrical conductivity of the space between stars. Unlike the dynamic magnetic fields found in stellar atmospheres or planetary magnetospheres, interstellar magnetic fields could preserve their configurations for millions or even billions of years, creating a sort of magnetic fossil record of long-vanished phenomena. Some of these magnetic fossils appeared to be the remnants of stellar magnetic fields that had been expelled into space when massive stars shed their outer layers during the final stages of stellar evolution. Others might have been created by the interaction of supernova shock waves with pre-existing interstellar magnetic structures, creating complex knots and tangles that could survive long after the original shock waves had dissipated. The most intriguing magnetic structures were those that showed evidence of having been shaped by processes that no longer operated in our current galactic environment. These ancient field configurations might have been created during earlier phases of galactic evolution, when star formation rates were much higher, supernova explosions were more frequent, or when our region of the galaxy had very different chemical and physical properties than it does today. The plasma wave archaeology revealed another temporal dimension to the interstellar medium that extended the reach of the Voyager's discoveries far beyond their immediate vicinity. Low-frequency plasma waves could propagate through the interstellar medium for thousands of years without significant attenuation, carrying information about distant events across vast expanses of space and time. The waves detected by both spacecraft included components that had been generated by stellar explosions, magnetic reconnection events, and turbulent processes that had occurred centuries or even millennia before the waves finally reached the Voyager's sensors. This meant that the spacecraft were not just sampling the current state of the interstellar medium, but were also detecting echoes and reverberations from a long history of astrophysical processes that had occurred throughout our local galactic environment. The wave spectra contained information about the statistical properties of supernova explosions, the evolution of turbulent structures in the interstellar medium, and the long-term changes in magnetic field configurations that had occurred over timescales that dwarfed human civilization. The chemical archaeology embedded in the dust grain measurements provided yet another window into the deep history of our galactic neighborhood. Different generations of dust grains carried chemical fingerprints that reflected the changing composition of the interstellar medium as successive generations of stars had lived, evolved, and died. The oldest grains contained relatively simple compositions, dominated by elements like carbon, oxygen, and silicon that could be produced by the first generation of massive stars. Younger grains showed increasingly complex chemical signatures that reflected the gradual enrichment of the interstellar medium with heavier elements produced by different types of stellar evolution and explosion processes. Iron-rich grains trace the history of type Ia supernova explosions, while grains containing unusual isotopic ratios of elements like titanium and chromium provided evidence for rare types of stellar nucleosynthesis that occurred only under very specific conditions. Some dust grains showed evidence of having been processed multiple times through different astrophysical environments, accumulating layers of different materials like cosmic sediments that recorded multiple episodes of stellar evolution and explosion. These complex grains were like interstellar archaeology artifacts that contained information about the long-term cycling of matter between stars, interstellar space, and potentially even the formation and destruction of planetary systems. The radiation archaeology revealed through the Voyager's measurements extended the temporal reach of their discoveries even further into the cosmic past. High-energy photons could travel through the interstellar medium for millions of years before finally being absorbed or scattered, creating a sort of fossilized radiation field that contained information about astrophysical processes that had occurred throughout the history of our local galactic region. Some components of the radiation field detected by both spacecraft appeared to be the accumulated afterglow of ancient supernova explosions that had occurred throughout the local bubble's history. The spectrum and intensity of this radiation provided information about the total energy input from stellar explosions over millions of years and the efficiency of different processes for converting supernova energy into observable radiation. Other radiation components seem to trace the history of star formation and stellar evolution in our galactic neighborhood. The infrared radiation from dust grains heated by starlight contained information about the stellar populations that had existed at different times in the past, while ultraviolet radiation signatures revealed the evolution of hot, massive stars that had short lifetimes but dominated the radiation environment during their brief existence. The cosmic ray archaeology was perhaps the most direct connection to the violent history of our galactic environment, since these high-energy particles carried information about the most energetic astrophysical processes that had operated throughout the local bubble's evolution. Different energy ranges of cosmic rays had different characteristic lifetimes in the interstellar medium, creating a sort of temporal sampling of particle acceleration processes that had occurred over different timescales. Low-energy cosmic rays with lifetimes of thousands to tens of thousands of years provided information about relatively recent supernova explosions and other particle acceleration events. Higher energy particles that could survive for millions of years in the interstellar medium carried information about more distant or more ancient acceleration processes. The highest energy cosmic rays detected by the Voyagers might have been accelerated by processes that occurred millions of years ago in very distant parts of our galaxy. the energy spectra and chemical compositions of these different cosmic ray populations created a sort of particle physics fossil record that extended far beyond what could be studied using any terrestrial accelerator or detector. The natural particle acceleration processes operating in our galaxy could achieve energies and create particle populations that were impossible to reproduce in any laboratory, providing unique insights into fundamental physics under the most extreme conditions. The gravitational archaeology accessible through the Voyager's trajectory measurements provided information about the mass distribution and dynamics of our local galactic environment over much longer timescales than direct observations could reveal. The current gravitational field configuration reflected the integrated effects of stellar formation, evolution, and explosion processes that had been operating for billions of years. Subtle variations in the gravitational field strength and direction contained information about the distribution of both visible and dark matter throughout the local bubble and surrounding regions. These gravitational signatures could potentially reveal the locations of ancient supernova explosion sites, the trajectories of massive stars that had been ejected from stellar clusters, and even the distribution of primordial dark matter structures that had influenced galactic evolution since the early universe. The long-term stability of both Voyager missions had enabled the detection of temporal variations in the gravitational environment that might be related to our solar system's motion through large-scale galactic structures. Our 230 million year orbit around the galactic center carried us through regions with different stellar densities, dark matter concentrations, and historical supernova rates that could create detectable variations in the local gravitational field. The technological archaeology represented by the continued operation of both spacecraft decades beyond their design lifetimes provided insights into the evolution of engineering design philosophies and the unexpected resilience of well-engineered systems. Components that had been designed using 1970s technology and manufacturing techniques continued to operate reliably in environments that were far more challenging than anything their original designers had anticipated. The evolution of mission operations procedures and data analysis techniques throughout the extended Voyager missions had created a sort of institutional memory about how to conduct complex scientific investigations over timescales that exceeded individual career spans. The lessons learned about project management, international cooperation, and knowledge transfer had influenced the planning and execution of subsequent major space science missions. The cultural archaeology embedded in the golden records carried by both spacecraft represented humanity's first attempt to create a truly permanent cultural artifact designed to survive for millions of years. The selection process for the contents of these records had forced humanity to confront fundamental questions about what aspects of our civilization were most important to preserve and communicate to hypothetical alien intelligences. The records contained not just scientific and technical information, but also music, art, literature, and personal messages that captured something essential about human culture and values during the late 20th century. They represented a time capsule of human civilization at a particular moment in our development, when we had just begun to explore space but still retained the wonder and optimism that had motivated our first steps beyond Earth. The very existence of these records raised profound questions about the nature of communication across cosmic distances and timescales. Any intelligence that might someday encounter the Voyagers would be confronting artifacts from a civilization that might be long extinct, trying to decode messages from beings whose thought processes and cultural assumptions might be completely alien to their own experience. The philosophical archaeology revealed through the Voyager discoveries had implications that extended far beyond astronomy and space science to influence fundamental questions about the nature of knowledge, exploration, and human purpose. The missions had demonstrated that the universe was not only knowable, but was actively communicating with us through the physical processes that governed its evolution and structure. Every measurement made by both spacecraft was a form of communication between humanity and the cosmos, a dialogue conducted in the universal languages of physics and mathematics that transcended the parochial boundaries of human culture and experience. The Voyagers had shown that science was not just a tool for manipulating the natural world, but was actually a means of participating in cosmic processes that operated on scales that dwarfed human experience. The discovery that boundaries in the universe were not sharp divisions, but rather complex transition zones, had implications for understanding boundaries of all types, from the interfaces between different physical systems to the boundaries between different ways of knowing and understanding the world. The Voyager discoveries suggested that reality itself might be more fluid and interconnected than our everyday experience suggested. The demonstration that seemingly empty space was actually filled with complex structures, dynamic processes, and information-carrying phenomena had profound implications for understanding the relationship between emptiness and fullness, simplicity and complexity, isolation and connection. The Voyagers had revealed that the universe was far more densely packed with interesting phenomena than anyone had imagined, even in regions that appeared to be completely empty. The longevity of both missions had provided a unique perspective on the relationship between human timescales and cosmic timescales, revealing processes that operated over decades, centuries, millennia, and millions of years. This temporal expansion of human perception had implications for understanding everything from environmental change on Earth to the long-term future of human civilization itself. The international cooperation that had characterized both missions from their inception had demonstrated the potential for transcending national, cultural, and ideological boundaries in pursuit of common goals that served all humanity. The Voyagers had shown that our species was capable of undertaking projects that required sustained cooperation over timescales that exceeded individual lifetimes and political cycles. The educational and inspirational impact of both missions had created a sort of cultural transmission mechanism that carried the excitement of scientific discovery across generations and around the world. Students who had been inspired by the early Voyager planetary encounters had grown up to become the scientists, engineers, and mission planners who were still analyzing the interstellar data decades later. This generational continuity had created an institutional memory and cultural momentum that enabled long-term scientific projects to survive changes in political leadership, funding priorities, and technological paradigms. The Voyagers had demonstrated that humanity was capable of undertaking truly multi-generational projects that could maintain their scientific and cultural relevance across timescales that approached the duration of entire civilizations. The legacy implications of both missions extended far into the future, since the spacecraft themselves would continue their journey through interstellar space long after human civilization might have evolved into something completely unrecognizable or might have disappeared entirely. The Voyagers represented humanity's first attempt to create artifacts that were truly designed for cosmic timescales rather than human timescales. In millions of years, when both spacecraft had traveled far enough to encounter other star systems, they would carry information about a species that had briefly flourished on a small planet orbiting an ordinary star in one particular spiral arm of an ordinary galaxy. They would serve as monuments to human curiosity, ingenuity, and optimism that would outlast not only their creators, but potentially the entire solar system that had given them birth. The story of what Voyager detected at the edge of our solar system was ultimately a story about the transformation of human consciousness through direct contact with the infinite. The missions had taken us beyond the comfortable boundaries of our home system and forced us to confront the true scale, complexity, and strangeness of the universe that surrounds us. They had shown us that we were not isolated observers of cosmic processes, but active participants in a galactic community that extended far beyond anything our terrestrial experience could have prepared us to understand. They had revealed that the universe was not a collection of distant, irrelevant objects, but rather a vast, interconnected system of which we were an integral part. The Voyagers had taught us that exploration was not just about discovering new places, but about discovering new ways of seeing and understanding our relationship to the cosmos. They had shown us that the boundaries of human knowledge were not fixed limitations, but rather temporary horizons that could always be transcended through courage, curiosity, and the willingness to venture into the unknown. And perhaps most importantly, they had demonstrated that the universe was not indifferent to human consciousness, but was actually structured in ways that rewarded curiosity, rewarded careful observation, and rewarded the patient accumulation of knowledge over long periods of time. The cosmos had revealed its secrets to the Voyagers precisely because they had been designed and operated with the persistence, precision, and dedication that cosmic scale phenomena demanded. As both spacecraft continued their eternal journey through the galactic night, they carried with them the dreams and aspirations of an entire species that had dared to reach beyond the safety of its home world and embrace the infinite frontier of space and time. Their discoveries at the edge of our solar system had opened not just new chapters in scientific knowledge, but new possibilities for human consciousness itself.